What about 8? No. It would create a huge cycle right here. What about 9? Same argument. It would create this little trapezoid here. What about 10? Right. It would create a cycle A, F, E, E. And 11, yes. Nice. Okay. So do you guys think that the minimum spanning tree given by Prim's is going to be the same as Kruskal's? Okay. Is that generally true?
If there's a unique MST, then surely.
Okay. I like that. Okay. So just random little tidbit. If there is a unique MST, Kruskal's and Prim's will find the same thing. If there's ties, all bets are off. Okay. But they will find a correct MST. Okay, so let's walk through Prim's. So the idea for Prim's is repeatedly try to bridge the cut. So right now I'm building from A. So the edges that are connected to either A or B are the ones under consideration. What would be the smallest edge that either touches A or B? It would be 3. I like it. Does everyone see why? Okay, I like it. Okay. So now, what is the next smallest edge that touches either A, B, or F? It would be 2. I like it. What's next? It touches either A, B, E, or F. 6. Okay. What's next? So I'm looking across this cut now. What's the smallest one? 11. Good. And what's after? 7. Nice. And then finally 4, right? Great. Okay. Okay. So we're going to move on to next question, which is a little bit more tricky. Yeah.
Do both of these terminate once all edges are connected, or does any one of them keep going?
Yeah, so you know that you're going to add at most E, the number of edges, minus 1, or sorry, V minus 1 number of edges. So as soon as you've added that many edges, you can stop. Yeah. Okay. So the next question is asking about what happens if we were to increase the weight of one edge or decrease the weight. So the idea that you'll want to apply here is what we're, yeah.
We can ask a question.
Yeah, sorry.
Why do you after the 2 add a 6 and not the 2?
Why did I add 2 before 6?
No, the 6 instead of adding an 8.
Instead of adding 8. Yeah, let's take a look at it. So we added 2, 1, 3, 2, and then 6. Okay, so at that point, the only things in our MST at the time were B, A, F, and E. So the cut that I want to look at is this cut, right? So I'm going to draw a little dotted line. I know by the cut property, I'm going to pick the smallest edge that bridges this cut. So the edges under consideration are 13, 12, 16, 9, 8, 6, and 14. So the smallest one must be 6.
So you don't just look at the smallest weight from your
the smallest weight from your...
from E.
Oh, not necessarily from the last thing that you added. It has to be from all the nodes that you have. Yeah, that's good. So in general for prims, you want to consider all edges in your current, from your current MST not just the last perfect cut. Okay, I think I saw another hand. If anyone cares to raise it again. No? Okay. Or not? Okay, that's okay. So let's quickly talk about the cut property. So like we were saying, like Noah and I were discussing, the cut property is such that if I look at any cut, the edge that bridges the cut is the smallest weighted edge. For any cut, the edge in MST is this. Okay. Any questions? Okay. So for parts C and D, small head for C, you're going to want to make an algorithmic argument using intermediate steps of Kruskals. And for part E, you might want to take a look at Prim's is the one that I consider, but you can also consider Kruskals. Okay. I'm going to give you a few minutes to work on it. If anyone has questions, raise your hand, and I'll try to walk to you. Okay. Yeah. Yeah, so for instance, for this consideration point, yeah, for part C. So you're considering CF, right? So you know that after you've added F in your algorithm, right, you want to consider all the cuts, and if adding or modifying the CF weight would cause you to choose it instead of another weight, right?
How would you go about making that cut?
Yeah, so for instance, the point in which we added F, right, was after we did 180. So at that point, I'm looking at this cut, right? So I would say that is 13, 12, 16, 9 to 10, 6, 14 to like this. Well, if I made CF 1.5, I would choose that before I choose that. And then you can make that similar argument as the stuff you do.
Thank you.
Actually, doesn't matter. Yeah. Okay, let's regroup. So for parts, does anyone want to throw an answer out there, and then we can like explain and walk through it? For part C. Yeah. 10.5. Yeah, exactly. That's great. Okay. So let's think about this. The MST that we found looks like so, right? I'm just gonna copy over the edges. So for AB, I want to consider when it would not be in the MST. So if I think about the order in which Kruskals would select these weights, at some point, AB wouldn't be in the consideration, right? So, for instance, if I change AB to 1.5, I know that I would add it because it would still be the minimum weight, right? So it would be the first thing that I would add with Kruskals. So that cannot be an answer. What about if it's 4.5? So I know that I would still add 2, 3, and then I would add 4. If this edge were 4.5, would it be added to the MST? Yeah, because that's the next highest edge weight, and it would not create a cycle. What about for 7.5? I would add 2, 3, 4, 7, and then again I would add it because it would not create an edge, a cycle. But if I add 10.5, if I created AB is 10.5, I would do, sorry, it would be 3, 2, right? I would add 4. I would not add 5. Where's 6?
On the right.
Partially cross out. Oh, right here. Yeah, yeah. I would add 6. So 1, 3. 2, 3, 4, 6. I would still add 7. And then the next highest edge weight would be 8. And I would add 8, not 9. And let's see. And then you're done. Right. Well, I think I did something weird. Sorry. Wow, moment of silence. Okay, so if AB were 10.5, I would no longer choose AB, and instead I would choose EG to be in my MST. Okay. Does everyone see that? Does anyone have questions about it? No. Okay. Okay, so now let's consider part D. For part D, what were people's answers? Yeah. All. Yeah, that's right. So I want to consider when I decrease CF to a new value. So let me switch this back to 1. So using Prims, for example, I would want to consider every single cut after F has been added to my MST, right? So remember, the order in which we added edges was 1 and then 3, right? So here's this. So after I've added 1 and 3, F is in my building MST. If I change CF to 1.5, I can look at the cut A, B, F, and 1.5 would get selected, right? So 1.5 must be a possible answer. What about if it's 4.5? I know that it would get selected after EF, because 2 is smaller than 4.5. So I consider the next iteration. A, B, E, F, the cut that spans it is this. And 4.5 would cause Prims to choose it. You can make that same argument repeatedly and you would find that all of the new edge weights would still work and cause CF to be added to the MST. Does anyone have questions? Yeah.
Can you make the Kruskal argument for this too?
Yeah, okay. So say it's 1.5. I see that I would add 1, 2, sorry, 1, 1.5, and then 2, and then so on. And then for 4.5, I would add it after these 3 edges have been added, and after CH. And you can do the same thing. I think if you tweak it all the way up to 10.5, at that point in your building MST, you would have all of these edges, and then 10.5 would still span this cut because it's less than, or it would be the minimum spanning edge across this cut, and I would not choose 11.
For your Prim's argument, when we were thinking that CF was 1.5, how come you included ABF? Wouldn't it just be AB at that point?
Wouldn't it just be? So you want to consider when C and F are in like opposite sides of the cut, right?
Okay.
So if I only look at A and B, C and F are in the same side of the cut.
So you automatically just have to include that one?
You would automatically
Just have to include F?
Yeah, you would like want to consider the first point in which F is on a different side of C. Yeah. Okay. Does anyone have any other questions? Okay. Let's move on to ternary search trees. Can someone give me like a 1-line reminder of what a ternary search tree is?
Try.
Oh, try. Oh my god. When I see IE, I think 3.
Right?
Anyway, yeah, does anyone want to give me like a 1-line reminder of what a TST is? Kate. Yeah.
So it's a way of representing strings where directly below the link to the node below is the next character, and then the links to the right and left there are alternative choices for that same location character.
I like it. So I'm going to represent this graphically. Alternative choices for next character. And if I go down, take this character. So it looks like a trinary tree. So at each node, you can have at most 3 branches. And like Kate said, it represents string objects. It might be like a bit string, it might be like what you think of alphabet strings, but there must be some notion of comparison. I'm going to give you like 5 minutes to work on the next question, and then we'll regroup. This one is like a little bit tricky, so I would highly encourage you to talk to your neighbors. And the order in which we'll like group together the answers is we'll do A, B first, and then C is talking about our weight tries, so if you don't get to that one yet, don't worry about it, we'll come back. Okay. So, Phil, talk to your neighbors.
I'm sure about this, but I don't see that I'm like, oh, there's like form,
Oh, I didn't think so.
yeah, exactly. That's as far as my Wait, are we not assuming that A is? Oh, okay. Smart.
Actually, I was like, well, I tried this, I tried to
I think that it's intuitive. I don't. But that you have.
If we print it today.
This is our last day. Yes.
Hopefully no one else will show. So I think.
Yeah, hopefully.
Yeah, I think so. Yes. Because like, actually, yeah, I think it's like you get M and then A, and then H, and then G, and you have this like straight line.
Or I can just go grab up the wire that is the copy. I just.
Have we learned about an algorithm that takes a set of strings before being inserted into a TSP and sorts them in a way to minimize the height? That's going to be our design question. I bet it's going to be our design question. I'm going to ask her. So, Lisa, I have a quick question. Have we learned about an algorithm in class that like sorts the a given set of strings before being inserted into a TSP such that it minimizes the height of the TSP?
Not necessarily.
Okay.
Yeah, so this one is more of like a stare at it and hopefully the like CS gods have come descended grace you knowledge. Yeah. There's no we'll talk about heuristics for like or intuitively what you want to do. But there's no like sorting.
But like, does there exist one that you know of, or?
Not that I know of.
Okay.
Yeah, I think it really varies. And yeah, I think like in like general application, people are pretty happy with the average or expected height of TSTs. So like, I guess the only real desirable one would be like the minimum height one. But I don't know so far. Okay. Wait, let's go over. Okay. Okay. Cool out. Let's talk about the minimum height first. Hi. Okay, let's talk about the order of insertion that would minimize the height. So notice that we only care about like the resulting height of the TST. So if you're randomly inserting things into your tree, don't worry about it because we don't care about the actual order of the strings. Intuitively, what you want to do for this question is not have too many like standalone danglies. Let me explain. So in a TST, it looks like a trinary tree, right? So think back to nice trees that you've seen in the past. For instance, if you're talking about BSTs, you've seen bad BSTs and good BSTs. What is a good BST? It's balanced, yeah. Can you phrase it in a little bit different way? Like maybe how it looks like?
So it's pretty symmetric if you look at all of the leaves.
Yeah.
Pretty much all the same.
Yeah. So you're bringing up this notion of bushiness, right? So you don't have any like long strangly bits all on one side. You want everything to be filled before trying to fill up more space, and that'll minimize your height. So same idea here. For a TST, the only things that I'm really in control of is when I have to consider alternative choices for my current character. because at some point I have to take characters, so this one I can't really like focus on. So in this case, I would want something to my left and my right if I can control it. Intuitively, you would think that if I started from, say, somewhere in the middle of this string set, say with an M letter, then I would have like S on one side and H on the other side. And I would have this notion of bushiness. Okay, so I'm going to give an example of a tree, and then hopefully you'll be convinced. So say I put M in the middle, and then, like I was saying before, G to one side, S to the other. What should go to the left of G as the first letter?
A.
A, yeah, A. Okay, great. And then what about the other side? H, right? Okay. So in terms of the first letter, this would be the bushiest that I could get, right? So let's try to fill in the other words. Say I were to add something like Maya, it would have to go straight down, right? So it would force my height to increase by 3, right? So in total I have a height of 4 so far. What else? If I add Mark, it would be MA, and then I would have to go RC, right? And so on. I know in this case that the lower bound on my height would have to be 6 because A is the lowest point for the first starting character, and I need 3 more nodes to at least insert RV. Okay. Can I do any worse? Like, does the height get any worse than 6 for like the minimum height? I'm seeing some shaking. Does everyone else agree? So my claim for an answer is 6. Did anyone get anything else? Yeah.
I thought we were considering the notion of try that starts with A at the top. Or is that not the case?
So not necessarily. This is just giving you an example of what the height would be. Yeah, that's good. That's good. That's a good clarification. Yeah.
So to pick which one to start with, like you picked M because most of the words are enough? Or how did you pick M?
Right. So this is going back to that notion of bushiness, right? So in order to maintain the bushiness of my TST, which would subsequently give me the smallest height possible, I need my first character to be somewhere in the middle of like the sorted order, right? So I have for my first character A, G, H, M, and S. And if you think back to like that notion of bushiness, you would like start filling in the next level, something like that, right? So my claim is like, oh hey, notice that if I put A here, G here, H here, M here, and S here, that satisfies bushiness at least for the first character. If you try to insert all the remaining characters, you would actually have that the height does not go past 6. Yeah. Yes.
Is there like a kind of systematic way of proving that it's the best? Because like since H is in the middle, then
Right.
you think like you want to start with H, but then you actually start with M, then there's more M's. Like,
Right. So it still has to be in what's it called? Everything. Well, the characters to your left are smaller, like isolated to that like node, right? And then to the right must be bigger. So in that sense, you can think about like, oh, what was the logic that I used for binary search trees that would give me like some notion of bushiness. It wasn't always just picking the middle one, right? You certainly could. I think in this case you might be able to get away with it. But as long as you find like something bushy, it would be good. Did that answer your question? That was a very roundabout way of going about it. Kind of. Okay. Yeah. If you look at what would happen if you started off with H in the middle, it would be you would have A and G, right? So say you had like M here and S here. A, G. I think you would have like the same initial height for your tree in that case. Did you have a question?
Yeah,
Yeah.
in some exams and in the class, he was saying that when there's an empty node, you found it at 0, and then here it's 1. Is there a rule that we should be using? Should the rule just specify?
Yeah, so there is a little ambiguity for like this notion of height. If there is any ambiguity, it'll be specified on the exam. But that's a great question because you saw in Jeopardy that like a single node is a height of 0. But like it specifies here, we're counting nodes and not links. Yeah. Yeah.
For context, if the words had different lengths, would our strategy change?
Yeah, it would get real messy real quick. Yeah. Yeah.
What was the question again?
Right. So the question was, if I have varying lengths of strings, would our strategy change? The answer is yes. Things would get a little bit crazier. You would want your longer length strings to be somewhere in the middle, right? So everything is dangling off of it, and that string won't increase the height as much. Okay. Let's move on to D really quick because I don't want to take up too much time. I'm so sorry. Okay, so the order in which we maximize the height. So we want to take the opposite strategy. We don't want balance, right? We want to force everything to one side or the other, and not have like both side action. Okay, so did anyone get an answer for this? Yeah. I got something higher. Yes. Also higher.
10?
10, yeah. Okay. So I'm gonna draw out this tree really quick. I wish that there was something like more systematic than just like trying it, but I'll show you like maybe some process. Okay, so so not gonna lie, this one took me a lot of staring, and for a while I was stuck on 9. So for anyone who was stuck on 9 as well, here's what happened. Okay, can I take a gander at like your 9 solution? Sure. Okay. Yeah. So initially, what my mindset was okay. Let me try to force everything to go to one side as long as possible, right? So one strategy of doing so is just by inserting in order. Remember, for something like a BST, that was going to give you your worst case height, right? If you just insert everything in order, you're going to dangle off all on one side. So a similar idea here. But what you end up with is A, G, H, M, and then S. You'll notice that for this M part of the trie, it's the longest part. And if you had M here instead of S, you would be shoving this part of the tree upwards, and it would not increase the height as much as possible. So visually, if you have like some part of your tree that's like this big of a triangle and this big of a triangle, you can increase your height by like rotating it a little bit into this, and then maybe like something like this. Does that make sense? Yeah. Okay. Does anyone have questions? Unfortunately, this is one of the questions that you just have to like churn it out and see how you can like rotate the tree to get something taller. Okay. Let's quickly talk about C together. So for an R-way trie, recall that it's different from a TST because the height of it will be the height of your longest string, or the length of your longest string, right? So an R-way trie, you start with your root, which contains nothing, and then say you wanted to add your character, you would construct an array for it, and your first character would go in the next level. So say your first character is A. And then you would add a new array for that A. What is the height of our R-way trie? 5. Exactly. So we see that the longest string that we have is length 4. So I'll need at least 4 nodes for that. But I also have a node for the root. So both the minimum and the maximum height of my R-way trie would be 5. Yes, Kate? It doesn't. Yeah, I know, it's weird. You just keep a pointer to the first character node. Yeah. Yeah, so in this question, it asks you to count nodes in the longest path instead of links in the longest path. Yeah, good. Yeah, sure.
So the thing differentiating a three-way trie and a TST is the fact that there's a root node?
So an R-way trie is different from a TST in that it occupies a lot more space, right? Because at each node, you're initializing an array that is the size of your alphabet. Whereas here, this is like very memory light, like LITP light, in that you only store characters as they come in. You don't initialize space for potential characters. Yeah. Yes?
Does that mean for all the tries, usually the minimum and maximum are the same?
Yes. Yeah, exactly. That's good. Yes?
So is there only one R-way trie for this given set of strings?
Yeah. Like, no matter which order that you insert it in, it'll result in the same R-way trie. And you can, like, mechanically do so for, like, a small subset of the strings to put into a string. Yes?
In what cases would the min and max not be the same?
In an R-way trie, it would be the same.
Always?
Always. Right. Because for an R-way trie, the height of your tree corresponds to the longest string that you've inserted. And you can't do any better or any worse. Yeah. Okay. Other questions? Okay. If there's anything that you took away from this problem, R-way is a guaranteed height, which is really good. A TST, not always guaranteed height, but very memory light. Okay. Yeah. For our way try, it was 5 and 5. Min and max.
Okay, so that's MSTs and CSTs. The next problem we're going to do is problem 6. So it's the problem about data compression that starts on the bottom of the next page. The first part deals with finding the compression ratios for 3 different compression algorithms we talked about in class: run length encoding, Huffman, and LZW. This problem. And then the parts B and C are doing some Bernoulli transforms and inverse transforms. So take 5 minutes, figure out the compression ratios for these. You can work with a partner if you'd like, and we'll talk about it.
Sorry, I was just wondering. I'm stuck on this one.
Oh, so we're not doing 5. We're going to be doing 6.
Okay.
I can.
Is it? So you know, like if you have an A, you want it to be followed either like by nothing.
Wait. Let me read the question first. Oh. Okay. What were you saying?
Like, if you have an A, you either want it to be followed by nothing or another A or a C. But then like, and then you might have like an empty string, so like you have to do that. But then like, if you have a B, you have to have a B somewhere. So then like, it kind of like gets rid of that. The fact that I feel like they kind of like the cases kind of run into each other.
Yeah. So you could include like another or for that, right? So it's like strings containing A, B, or C. So if you know like, oh, if I have an A, I don't want this to happen, but I can have a B, so I can or it.
But I think like the problem I'm having is the fact that like after an A, you might run into nothing, right? Just like, so it could be like A and then it could end. So, but then if you do like an or, then you have like a B, then you can say like A and then end, and then you could do a B.
I don't think I'm understanding. Wait, sorry. So you're saying, so if you do...
I don't think that would work.
So what this is saying is you can take either A with either C or A or C afterwards,
Okay.
or you can take B.
But then like, but then you have to do it again though. Like you have to put this under star.
And that's okay.
But then you could choose A, star, then go back, and choose a B, and you have A, B. I think that's the one problem that I've been running into.
I see. Yeah. Have you guys learned greedy symbols?
What?
I think there might be a way of getting around that if you do something greedy. But I don't think you guys have learned that. Yeah. Let me check this for you.
Alright, thank you. Sorry.
No, you're good. Try flipping the orders.
Okay.
Try creating an expression that uses these
Like, wouldn't that like ultimately do the same thing though? Because like, if you have like A and then AC, and like that, and then you do that in the star, you could do the same thing with it. You do B, and you can do an A, and you can do a B again.
Fair. Let's
Let's just say your new like you interpreted
divided by maybe.
some single thing like this one did.
So say try writing out a few strings that are possible under these constraints, and then pick the pattern. Namely, you'll find that if you have an A, it must be followed by C if the string continues, or the string ends.
Can't an A just be followed by another A?
Yeah, it could be like, but after a sequence of A's, right?
Okay.
It must be followed by C.
Oh, okay.
Yeah.
Right, thank you.
Yeah, I think you might be able to get that right.
Okay, so even if it's like n equals 2, I'm just not enough, and like n is large enough that I can get the equivalent thing.
I don't know. I'm just like thinking that the ones that I do now.
And since it's so long, that's
If I hang off with an
it's
A,
fine because they're all
right, then your A's would be encoded in 12 bits.
part of the
So you would be
Yeah, one means 8-bit,
Very close. It was on 1928.
okay. So you're
Am I
like
forgetting the A's?
yeah, exactly.
So,
Nope, it's actually not the it's actually how many characters you have.
which is
Oh,
what
okay.
number?
And then on this side it's these characters
okay.
and then you just like you construct it this way and they're just like
That was
yeah. Oh yeah.
Sorry.
Alright, so in the interest of time, let's start talking about data compression. So the first two of these deal with run length encoding. Can someone give me a quick description of run length encoding? Yeah, and someone?
So for sequences of zeros and ones, it will encode how many zeros there are up to 255, and then how many ones there are.
Exactly, yes. So the way this works is we're going to take a sequence of zeros and ones, so just binary digits, and we're going to convert that into 8-bit counts, which are alternating between zeros, counts of zeros, and counts of ones, starting with zeros. So we have these 8-bit counts where we have how many runs of zeros there are, how many zeros in a row, then how many ones in a row, then how many zeros in a row, ones in a row, so on, alternating back and forth. So for the first problem, we just have a sequence of all zeros. So if our sequence is entirely a bunch of zeros, what would we compress or encode this string of zeros as? Yeah, that's right. Cool. Yeah, that sounds good. So let's say that this was our first sequence of 255 zeros, you said. So because we're working with 8-bit counts, 255 is the maximum number of zeros we can represent in one count. So we'll take this 255 and we'll turn it into just 8 bits, which says, well, actually, if we have 255, this is going to be all ones. So this is just 8 bits. So these ones say we have 255 zeros. And then following this, after our count of zeros, we need a count of ones. And if this were our string, we had another 255 zeros after that. then we need to encode the fact that there's no ones in between. So that's going to be 8 bits of all zeros. And so on. So every set of 255 zeros is going to be followed by, or is going to be encoded as an 8-bit count representing all ones and another 8-bit count representing all zeros because we have no ones in the middle. So what is our compression ratio given this setup? So the compression ratio is always going to be, we have the original count, and over that, the compressed counts. So what's our original number of bits needed? So in these problems, you're always wanting to find some pattern in your structure, because whatever pattern you find that gets repeated throughout your input, the ratio is going to stay the same for each copy of the pattern. So we can look at one particular instance of our pattern and see what is the ratio for that pattern, and then that will be the ratio for the entire input. So given that, what's our ratio? Yeah?
255 zeros into 2 8-bit numbers, so it would be 16 over 255.
That's correct. Yes. So our answer is going to be 16 over 255. Because every sequence of 255 zeros we took in originally will get encoded as 16 bits. 8 bits counting the zeros and 8 bits counting the ones. Any questions on this? Yeah.
Can you please clarify what you mean by 8 bits counting the ones?
Yes. So because run length encoding contains alternating counts between zeros and ones, so you always have to have 8 bits that say how many zeros in a row, and then 8 bits for how many ones in a row. And then you'll keep doing this alternating between zeros and ones. So we can encode all of these zeros together in one count, and this is the maximum number of zeros we can encode. But we have to say something about the fact that there's no ones right here, because whatever is reading the run length encoding is expecting that this count for zeros is going to be followed by a count for ones. So we have to include these 8 to say there's nothing. Cool. Okay, how about part 2? So in part 2, we have a sequence of alternating zeros and ones. On and on forever. And we're still using run length encoding. So what's going to be our encoding for this kind of string? Who wants to try? Yeah, Kate? So you're saying every bit's going to be represented by an 8-bit count.
Okay, no, that's not the answer, but I'm going to why it's not the answer. Because you have one number, and then it's like, okay, there are this many zeros,
Mm-hmm.
and this many ones, but you only have that as 2 numbers, so it's 2 8-bit counts.
So it's true that every character, every bit in our input is going to ultimately get encoded into a series of counts, which are 8 bits long. So if we start out counting how many zeros are at the start of the string, well, there's just one. So this 0 is going to get encoded as these 8 bits to say that there's just 1 0 in a row. And then this 1 is also going to get encoded as 8 bits to say that there's 1 1 in a row. So this is our smallest instance of the pattern here, this alternating zeros and ones that repeats forever. And within this pattern, we've turned one character, or 1 bit specifically, into 8 bits. And same for the ones. So what's our compression ratio? It's actually 8. Yeah, this is really bad because our compressed number of bits is 8 over our original was 1. So we've actually increased the size of our data by a factor of 8. So this is really bad. So what have we learned about run length encoding? Well, sometimes it really sucks. And in this case, it sucks because we don't have any runs at all. So run length encoding is good when we have a lot of runs of repeating digits. If we don't, then it's bad. Okay, the next two parts deal with Huffman coding. So, part 3, we have this sequence. AABC, AABC, AABC. And we're going to encode this using Huffman encoding. So, tell me a little bit about how Huffman encoding would apply to this text. First of all, what is our pattern? Someone? Yeah, AABC. Cool. So this is the smallest instance of our pattern. So for the purposes of our compression ratio, we're going to focus on this AABC. Okay. Now, someone describe to me what Huffman encoding will do to this pattern. Yep. Okay, so it's going to construct a trie of our characters, and the trie is going to tell us what the encoding for each character is, right? Now, what does the location of a character in the trie depend on? The frequency, yeah. So in Huffman, we're dealing with the frequency of characters. This is sort of the defining feature of Huffman encoding, where more frequent characters are going to receive a smaller encoding. So looking at our pattern, we need frequencies that all sum to 1. So what are the frequencies going to be of A, B, and C? 211. Okay, so A definitely appears twice as often. Yep. Okay, now make that sum to 1. Yep. So our frequencies are 1/2, 1/4, and 1/4. So now given these frequencies, Huffman encoding is going to construct a trie. And what's the process for constructing the trie? Given that we have these frequencies. What's the first thing we'll do? Yeah, Anton? Okay.
So wouldn't the algorithms find the two groups of lowest frequency, merge them, and then repeat to like form this trie?
Yes, exactly. So the process of Huffman encoding will actually not start with the A, but it's going to start with the B and C. So it sorts all these frequencies, and it takes the two trees so far with the minimum frequency and merges them together. So B and C have the smallest frequency. We will merge these and put a link here between them. And then this tree now becomes a frequency of 1/2. We keep doing this merging process until we just have a single root. So then we merge these like this, and we're done. So now we have the encodings for each character. So given this trie, A is going to be represented by the bit 0, B is going to be represented by 0, 0, and C is going to be represented by 0, 1. Did I write it wrong? It is, oh, sorry, these should be ones. Thank you. Cool. Okay, so now that we have our trie, we can figure out what the compression ratio is for a particular instance of our pattern. So originally, how many bits did it take to represent our pattern, AABC? 32, I heard. Yes. So originally we have 32 because each of these is 8 bits long. Note that we are now dealing with characters. I should have said this. So each of these is 8 bits long, not 1 bit as before. So we have 32 bits. And how many bits will be in our compressed version? 6. Yeah. So 3 over 16. Any? 6 comes from the fact that if we convert these into their Huffman encodings, this is going to be 0, 0, 1, 0, 1, 1. So 6 bits here to represent the characters that were originally 32 bits. Okay, part 4, Huffman coding for a random string. So if we try to compress a string of random characters using Huffman, what's going to happen? You can assume they'll all have the same frequency, right? And what happens if they're all with the same frequency? What's the height of our trie going to be? It's going to be, yes, it's going to be essentially log R. What we're going to get is if we merge everything with a perfectly balanced trie, it'll look something like this. Really, really balanced. And all of these are being encoded with the same number of digits, so we're not actually getting any compression ratio. But actually, looking beyond how Huffman works, in general, can you compress a random string of bits? No, you can't. It's theoretically impossible to compress a sequence of random bits because there's no structure in the data that can be encoded more efficiently. If it's random, there's no patterns or anything we can use to come up with a compressed encoding. So the answer is 1. Can't compress it. Yeah, Chris. It's for everything. So if you're given a random string, no compression algorithm in the world can compress it. People have tried and failed. Okay, let's talk about LZW now. Last 2 parts. So, our string, number 5, is going to be a sequence of repeating AB, 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 so on. And actually, let me draw a few more. Okay, so we're going to take this sequence of alternating A's and B's and encode it using LZW. So this one specifies a few more things. It tells us that the code words, the encodings in our LZW table are going to be 12 bits long. And it also says that we have a max of 2 to the 12 or 4096 entries, but that 256 of them are reserved for our alphabet. So because we are left with, because 2 to the 6 are reserved for alphabet, that's minus 2 to the 8, which gives us 3840. So 3840 is the remaining size in our code table that we're going to use for LZW. Now, what's this code table? So, would someone like to walk me through what happens if we start reading through this string and encoding it using LZW? So let's say in our table right now we have some code word for the letter A. Say it's like 40 and B is 41, let's say. And then this is our alphabet. It's already in there. And then we're going to start reading through this string and adding things to our code table. So what will we add first? So first, we're going to read this A. A will get encoded as 40 because we have that in our code table. Cool. And then what do we add to the code table? We'll add AB. Yes. So anytime in LZW, anytime you match the longest code that you have, you're going to take the following letter and add that to the code table. So we matched an A, so we're going to take A plus the next letter B and add that to the code table. So AB, and we'll give it a value like 80.
Is it 80 or 81?
Doesn't really matter. We can do 81 if that's what other slides have done. Sure. Okay, what happens next? So we're going to read the B now. Yep. We have B in our table, so we'll encode that as 41. And then we're going to add B plus the next character, which is A, so we'll add BA. Say 82. Okay, what next? Yep, so now we can read AB, which is 2 characters long. We'll assign that 81, and we'll read ABA. This will be 83 now. Okay, then what can we do? Now we can read ABA. Cool, so it's getting longer. And then we'll add AB, AB. Okay, what next? So we read ABA. Now we're starting at this B. Let me add some more characters to make it clear. So what's the longest string we can read now that's in our table? Yes, just the BA. So we'll do BA, and then we'll add BAB, 85. And then we can read BABA, or actually, we'll read BAB, and then we'll add BABA. Okay, and this process is going to continue. So what's the pattern here? We need to extrapolate some pattern of how quickly our table is filling up. Because we only have 3840 entries. And so far it looks like it's getting filled up with these alternating sequences of either starting with A or starting with B. So what's the pattern? How long are these eventually going to get before we run out of entries in our LZW table? Yeah?
It looks like about half.
Why do you say half?
Because it just alternates between ones that start with A's and ones that start with B's.
Yeah, that's a great point. So what we're doing here is we're building up 2 sequences, essentially. We're building up a sequence that starts with A, and then AB, ABA, ABAB, continually adding letters to this. And we're also building another sequence that starts with B's. That was all. Okay, so you can think of it as we're filling up 2 sequences in our code table, and you said we'll fill up at exactly half of the number of entries we have. So if we have 3840 entries in our code table, and we're filling up these 2 sequences, each of them is going to fill up with half of 3840, which is 1920. So what we're going to end up with is a sequence that starts with A's and a sequence that starts with B's that are each of length 1920. So this tells us the number of A's and B's in a row that we can encode, maximum. And then we run out of entries in our table. And just to be clear, this is, if we add these together, we're going to get the number of entries remaining in our table. Does anyone have any questions on this right here? This is key. Okay, so once we have these two sequences, now we can talk about the ratio. So once our table is completely filled up, what is the maximum size of our original sequence that we want to compress? If we have an infinite series of alternating A's and B's, we want to know what's the maximum number of A's and B's in a row that we can compress efficiently using our table. Because that's going to tell us what our ratio is as this goes on forever.
1,920 characters.
Yeah, so what we're going to get is, in our ratio, the maximum run of characters we can encode is 1920. So whether it starts with A's or B's doesn't matter, but this is our maximum length. So we're going to say that there are 1920 characters in a row that we can encode efficiently. And for each of these characters, how many bits do they take up? 8? Yes, it is 8. So we have to multiply this by 8 to get the actual number of bits that each character is encoded as. So this is 1920 characters, 8 bits per character. And what do we compress this whole thing down to? Just 12, yeah. Because the problem says each of these counts is 12 bits. So this is our answer, and then if you do the math, it comes out to 1 over 1280. Any questions on this? Yeah. The 12 comes from the fact that the problem specifies we're using LZW with 12-bit code words. So all these. Okay, last one is LZW now. With a sequence of n over 2 A's followed by n over 2 B's. Okay. Would someone like to tell me how to approach this problem? Yeah. Okay, yeah, that's right. So our table is going to fill up originally with all these A's, where we're going to get longer and longer sequences of A's, and then at the very bottom, when we run out of entries, we're going to have a sequence of 3840 A's. That will be represented by some number. Whatever. Actually, it'd probably be, whatever, 4,000. Okay, so let's say our table fills up with all of those A's. Then what?
Like, if we assume that the string is like long enough, most of the n over 2 A's are going to be encoded by like those 3 840 A's using 12 bits only. So like you divide n over 2 over 3 840 to find how many those you fit in the string, and then you multiply that by 12.
Okay, so for the A's, you're saying that just the encoding for the A's is going to be, we can take 3840 times 8 and compress those into 12 bits. But keeping in mind that part of the problem specifies that this is n over 2. So this is only half of our characters in the sequence. So the way to think about this is that we're actually going to multiply this whole thing by 1/2. This does not represent our entire sequence. This only represents half of our sequence. So this is going to give us the compression ratio for the A's, and that comes out to 1 over 2560, I think. Okay, now how about the B's? What's our compression ratio for the B's? Yeah. 12 over 8. So the compression for B's are really bad. We don't have any entries in our code table for sequences of B's, so we're going to get every character B, which is 8 bits, gets encoded as a 12-bit code word. So we've increased from 8 to 12. Now, again, just as with the A's, we have to multiply this by 1/2 because this is only half of our input sequence. And what we'll end up with is 3/4. So we have compression for A's, we have compression for B's, and because we take our string to be infinite, which of these is going to dominate? The B's, yeah. So as our string gets longer and longer, our compression ratio is going to get closer and closer to 3/4. So this is going to be our final answer, 3/4. Yeah.
Where did that 4,000 number come from to the left of B's?
I just made that up.
Okay.
It's just whatever the encoding is. Let's say it's X. As long as you know it's 12 bits long.
Okay.
Ignore the specific number. Yeah. Any other questions? Okay, so that's data compression. Well, actually, that's part of data compression. I'll give you a choice. Do you want to work through parts B and C, the Burrows-Wheeler transform, or move on to the next problem? Raise your hand if you'd like to talk about Burrows-Wheeler. Raise your hand if you'd like to move on to the next problem. All right, next problem. So the next problem is a partially filled KMP table. These are definitely some of the more challenging, or at least time-consuming problems on an exam. And there's a bunch of different heuristics you might use to solve this. So in this problem, you're given a partially filled KMP table, which represents some DFA for a string of length 10. So some pattern, length 10. Your goal is to figure out what the original pattern was, the row S, and also complete the first row of the table. So filling out row A. So I'll give you 5 minutes to work on this with the part. Is it okay if I erase this? Okay.
know that.
You know.
You should get that. Using that.
Oh, you got the whole table.
Oh, I don't. It's just like I think it's easier like to avoid mistakes.
No,
by
I
filling everything out.
totally agree.
Yeah.
In the interest of time, we probably won't.
Okay.
That's what I like. Good practice.
Yeah.
All right, let's start talking about the KMP table. So, when you come to these kinds of problems, there's a question of where to even begin. So, the first thing you should look for is any easy information that you can start filling out. So, where might be the easiest place to start putting in information? Given the info we have already. So at 3 and 4, what do we know, given these columns? Yeah, so anytime we see an edge going forward, that has to be a match in our DFA. That's the pattern we're looking for. So 4 and 5 both move forward a row, so we can fill in the fact that, yes, A is the correct character here. And B and C will take us back to 0. Okay, we can do the same thing at column 6. So the 7 moves on, so we know that B has to be the right match here. And we can do the same thing at 9, because we're given 10, so we can fill in C. Cool, so we've gotten some starting characters out. It's probably the first thing you should do when you approach this. Where do we go from here? You can throw out some ideas for places we can fill in info. Yeah.
In the 6th column of A, it says 2, which means that the last 2 characters you got are in the string. So AA is like the first 2.
So what you're saying is looking at some number in our DFA, that number always tells us where we're going to go, whether it's a forward edge in the case of a match, or if it's backwards, then we're backtracking. But the state you're at always determines what the previous characters you've seen are. So actually, I'm not going to start at 2 yet, but let's start at something easier than that. How about from columns 3 and 4? So what can we determine, given that these edges from B and C are zeros? What does it mean to go all the way back to 0? Yeah, Huffman?
Because for 3, both B and 0, 0, you know that 0 is going to be 1. My first character is going to be 1. A. And because of the 4th column, we also know that it's going to be A.
Nice. Yes, so from either one of these columns, we can use the fact that B and C are both 0 to figure out what should go here. Because if we go back to 0, that means that we haven't matched anything in the pattern. And we definitely haven't matched the first character in the pattern. So if we're not matching the first character at B or C, then we can tell that the first character needs to be A. So given that, we can fill in A for the first letter. Because if this first letter was B or C, then either one of these rows would not be 0. It would have been 1, telling us that we have matched the very first character, and now we'd be on this column, the second stage. Does everyone see that? So from these zeros, these guys here, we can infer that A is going to be the first letter. Okay, what else can we fill in?
Would it be the same thing for then column 1 because of column 4?
So for column 1, because of column 4, what does column 4 tell us?
That you have to go all the way back and
It just tells us that if we see a B or C at this point, so we can tell what characters we're trying to match. We're trying to match an A. And we can also tell what characters have come before it that we've just seen. But we're missing a lot of info here. We have an A, but does this A really tell us anything? Not yet. We can at least fill in this box to say that A is a match and these are zeros. So that's cool. What else? Amit?
Well, isn't it because we have 0 for B and C in column 4, we know that the beginning of the string is not going to be neither AB nor AC, so it has to be AA. Because it's sending us all
Oh! I believe you're right, actually. Yes, good point, good point. So, okay, going back to one of these squares. One thing that's interesting about KMP tables is you can always take a square and figure out what the last characters you have seen are based on that square. So if we look at column 4, row C, we can say that we must have just seen the characters that come previously in the table. So we must have seen A, blank, blank, A. And then, so that comes from the previous columns. We can figure out what we must have just seen. And then the last character comes from the row. So in all of these states, we have just seen A, blank, blank, A. Now we're at this column. And looking at each row, for example, in C's row, we can see that we've just seen AC. And if we see AC, then if this were a C, well, at least the AC would have matched here at the end, and we could have gone on to column 2. But because this goes back to 0, we can actually say that AC is definitely not the beginning of our pattern. And so we know this is definitely not a C. So we can fill in a 0 here. And we can actually do the same thing for this one, because this would say this is A blank blank AB. If we'd seen AB, we could have moved on to this column. But because it goes back to 0, instead, that means AB and AC are not prefixes of the pattern, which means that this character has to be an A. And so we can fill in this one. So typically the strategy when you're looking at KMP tables and you have some sequence, and when you want to find where to backtrack, the general strategy is you want to look for the longest suffix of what you've seen that is a prefix of your pattern. So given that at this square we would have seen A blank blank AC, we look at all of the suffixes of what we've seen and figure out, are any of those prefixes of our pattern? And that will tell us where to backtrack. We just take the longest such suffix. But if AC goes back to 0, then definitely this could not have been a C. Did you have a question?
I was going to say that by the same reasoning, because 9 on B you have a 3, you could conclude that 7, 8, and 9 are the same.
Yes, that's exactly correct. So given that this position says go back to state 3 is the state at which we have just seen these characters, A blank, and now we're here. So given that this says go back to state 3, we can determine what characters we would have just seen here. So we know that, for example, the first two would be AA, like before. So whatever comes before here, there's going to be some sequence of blanks, dot, 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 and then at the end, we will have seen A, and then, so that comes from the columns, these columns, and then the final character comes from the row. So because we're in row B, we're going to say this, we would have just seen AAB. So given that in this state we would have just seen AAB, and we move to state 3, we can say that, okay, well, B must be the correct string here. So now we can fill in this. Does everyone see what just happened there? We will not see what happened there. So you're always trying to figure out what the characters are that you've just seen from a particular square, and then figure out from what you've just seen what are the suffixes that would help you backtrack. And that will give you information about what the characters you've just seen in terms of your pattern. Because if you look at any state, that state tells you, or any column, that column tells you what are the characters you've just seen. Because you must have matched all correct characters to get up to that point. Okay, so we now almost have the entire pattern. That's cool. What other information can we fill in here?
I have a question.
Yeah.
For the second column, what would you do for like, what number would you put?
For here?
Yeah.
Yeah, so we want to figure out what goes in this box. Okay, so what should we put here?
2.
This should be a 2, right? Why?
Because like the sequence starts with an AA, and if it's a AAA, that's still like that same AA.
Yep. So in this box, we would have seen AA based on the previous 2 columns, and then from the row, we're seeing another A. So that is triple A's. And if we do this longest suffix, which is a prefix of the pattern, the longest suffix is going to be these 2 A's, AA. So we'll take these 2 and say that sort of a self-edge. We stay at the same position. Cool. What else? We're getting closer. What time is it, Owen? 12:59. So we have these 2 A's now. So let's fill in the easy stuff. So these definitely move us forward. So we're going to get 8s and 9s here.
How do you have them?
So these A's came from this 3. Based on the 3, we said that if we go back to state 3, we would have seen A, B, and so these need to be A's. Yeah, Huffman?
So if you look at column 6, you have a 2 for A.
Mm-hmm.
That means that the last 2 characters, like that character and the character therefore it must be A is at that point because they would have to match the first two column. So 5 would have to be an A.
That's right. Yes, this has to be an A. And the reason for that is at 6, what we would see is some string of characters followed by, based on column 2, it'd definitely be these two A's. So A, we see another A, the last 3 characters are A, so we can fill in this one here. Say this has to be an A. Cool, and then we can fill in this guy, because this is going to go to 6. And then at the 9, you do this process, again, of figuring out where to backtrack, and I think it's 6, actually, yes. So the longest suffix is going to be AAB, AAA here. This plus an A, which is equivalent to the one that starts here, AAB, AAA. So this is the longest suffix. That's a prefix of our pattern at the square, so we'll put 6 here. Okay, so it is 1 o'clock now, so you're welcome to leave if you need to. We will stick around, and I think we'll do the design question. Question 12, there's a graph algorithm design. So if you need to leave, that's cool, but if you'd like, stick around, and we'll do this design question. Okay. So for the last problem, question 12, this deals with a graph where you're given an unweighted directed graph, G, and we want to pick 2 vertices and figure out how many distinct shortest paths there are between those 2 vertices. So it's like a shortest paths problem where we don't just want one path, but we want to find out how many paths there are of that shortest length. So I'll give you some time to think about this one. Could you put that up on the... Yeah. BFS does not consider weights. Okay. Yes. Yeah. They're all sort of high. The difference is weight.
Yeah, okay. Oh.
It's faster to double.
Oh yeah. Wait. We get these. No, BFS should be.
As in like the number of edges.
Yeah, but like get Asians. Oh, so all I gotta do is find the distance to it, right? Find which proofs can be swapped. Like there's just if you have an Asian path, right? All you gotta do is say, okay, well, let's say like this is a short path. All you gotta do is find okay. Also, let's say I switch this point to this point. This is just sort of maybe how would you switch this?
Let's say the shortest round.
Oh, yeah, so this one.
Anyone want more time? Alright, let's start talking about it. So here's an example graph of where distinct shortest paths becomes interesting. So let's say we want to find the number of distinct shortest paths between S over here and T. How many distinct shortest paths are there? There's 4. Yeah. So for all of these cases, we can take this path up here, we can take this one down the middle, we can go here, go up and take this one, or go down and take this one. So there's 4 distinct ways to get from S to T. And we want to find a way to determine how many paths there are. So would anyone like to start us off with their thoughts? First of all, the problem gives us some information that this is directed and unweighted. So given this information, which algorithms would you start thinking about for finding a shortest path? Yeah.
BFS.
Why BFS?
Because there's no weights and gives you paths. And C plus V running time as well, which is what BFS is.
Cool, yeah. So BFS comes to mind whenever you see unweighted. BFS is our shortest paths algorithm that operates on a graph without weights. So if we don't have weights, we can generally use BFS. If we do have weights, we have to go to Dijkstra's or Bellman-Ford, which are weighted graph algorithms. But BFS is for unweighted shortest paths. You have a question, Kate?
So in general, when should we use BFS for things and when should we use DFS?
Well, anytime you want shortest paths, you're generally going to be using BFS. DFS can be used if you're doing problems related to connectivity or if you want like a topological ordering. But typically, anything with shortest paths we'll deal with BFS. Finding cycles is DFS as well. Okay, so BFS might be a good place to start. So normally with BFS, it just gives us the distance and one shortest path to a node. But now we need to find all shortest paths. So what do we need to add or modify about DFS in order to help us find not just one path, but all the paths, how many there are? We don't need to find what the paths are, just how many. Yeah, no?
Like every time you update it, you just tally it?
What are we tallying?
Like how many times you've updated it, because that will tell you how many different paths there would be.
Okay, so keep some kind of tally. It's an interesting idea. Yeah.
Well, maybe you could update a counter every time you DQ or NQ the neighbors, but and then maybe like decrement the counter when they don't reach T.
Sounds like we might have to do some backtracking if we go down a path and then find out later that path like doesn't get to T, like it's a dead end or something out here. To keep our runtime low, we don't want to have to do too much backtracking. Yeah.
You have like an array that keeps track of how many times you like match with the vertices. So you have mark or like mark you hit a vertices that's already marked, so then you know like at each stage like that one's been like the one like that goes to T that's horizontal has been marked like 3 times. When you get to T, you know like that's how many shortest paths.
Okay, so let's think about that for now. So what if we count how many times a node has been... So you're saying how many times a node has been marked. Typically when we talk about marking a node, when do we mark a node in BFS? In relation to this queue that we're adding elements to and dequeuing from, when do we actually mark a node? Not when we add it to the queue, when we dequeue it. Right. So we mark a node in BFS whenever we dequeue it. And how many times does BFS normally mark a node? Right. So BFS normally dequeues a node just once. And when you dequeue it, what do you know about that node? What do you know about the path that you found to that node at the time you dequeue it? Yes, yeah. So at the time that you dequeue a node, you know that that is the shortest path that you found. And this is a really nice property of BFS because it means that we don't have to visit a node twice. Whenever we dequeue a node, we know that that is the shortest path to that node, and we'll never revisit that node. And that's really useful for our runtime, because this only happens once. If we end up visiting a node multiple times, our runtime could grow much larger than B plus E. So we actually want to keep this property, that we're only going to dequeue a node once.
So
yeah.
What I meant with it is that like not when you dequeue or like mark it, but like when you check if it has been marked already, you like keep a track of how many times it's been marked.
So as opposed to dequeuing, you're saying keep track of how many times we see a node.
Yeah.
How many times we look at it.
Yeah.
Okay, cool. Yeah, so that's a good idea. So what if instead of count how many times a node's been marked, we count how many times a node has been seen. So what does that mean? So as BFS runs, if we start at node S, we're going to start by looking at all of its adjacent vertices. And normally we have some information. We have like an edge 2, we have a disk 2, and let's say we now add this count thing that counts how many times it's been seen. So let's naively just see what happens if we do this with DFS. So, and I'll give all of these nodes numbers. Why not? So if we start from S, then what we're going to get for 1 is we'll say, well, it has an edge from S, a distance of 1, and we've seen it 1 time. And we'll do this for each of its neighbors. Okay, so we continue this process, and let's say that we break ties in order. So we'll visit 1 next. So we'll take 1, we'll look at its neighbor, and we'll say, oh, now it has an edge from 1. Its distance is 2, and its count is going to be 1. We've seen it 1 time. Okay, now we've looked at all its neighbors. We pop off this node, BFS ordering, and we look at 4. And what should we check here when we're looking at a node that we've already seen?
Distance.
So we should look at the distance, right? So we need to actually compare these distances and see, okay, if this was our current distance to node 2 and we add 1 to get to 4, is this a better shortest path? Well, in this case, the distances would be the same. So what happens when the distances are the same? Yeah, we're going to increment the count, right? So all we'll do is we'll just increment this count on 4. Okay, and then we'll do the same thing from 3. So we'll look at its distance, we'll add 1 to it, compare that, it's the same, so we'll increment this count again. Okay, and we're also going to add this one. So this guy's going to have an edge of 3 at a distance of 2, and we've seen it once. Okay, now let's say we do 4, we look at T, and T, we're going to say, okay, it has an edge from 4, it's at a distance of 3, and what about our count?
We're going to carry that count.
Yes, so it's not just the case that we increment, but we're actually going to carry over the count from the previous node. So we'll take our count 3 that says we have 3 paths of shortest distance to node 4. We're going to carry that over and say, now we have 3 paths of shortest distance to T. Yes, so our counts are going to be cumulative. Right, so actually, we'll say, I guess, some counts here. So this was originally 0, and then we're going to sum it with the number of counts that we've seen from the previous node. So for example, if we now go from 5 to T, we'll say, okay, this path has a distance of 2 plus 1. It's the same, so we're going to take this count and add it to the 3 and get 4. And then this guy will have 5, 3, and 1. So does this work? Yeah, question.
Keep track of like carrying the count before
So you can assume the counts, all this information is stored in some table that we have access to. Yeah. Do you need edge 2? For this problem, not really, because we don't actually care what the paths are. We only care what, how many paths there are. And This edge to array is only giving us one path, so we actually don't really need it. We can ignore that. Really, all we need are the dist2 and counts. Yeah. Wouldn't you need edge2 to determine how to carry over the count? What do you think? Do you need it? Yeah. Oh, let's answer this question first. Do we need edge2 to keep track of the counts? I don't think so, because if you're looking at a node and you're looking at its neighbors, you know what that node is that you're currently at. So I think that's the only count that you need to look at. So yeah, this solution sounds good. So one thing to be careful about is the shortest path. So for example, if let's say we found a better distance to this node that was at like a distance 1, what would we do to the count? We'd replace it. Yeah. So if the distance is less than the best, we're going to replace the count. If distance is equal to best, we're going to sum. Cool. And otherwise, this is pretty much running like BFS. So we end up with a nice B plus E runtime. Thank you, BFS. All right, we'll finish up there. If you have any other questions, you can come up and talk to us now. Otherwise, good luck on the exam. Get some sleep.
So the same thing since like technically we are visiting the state it works on so would that not work okay. So in an MC
So like if you extend this to an arbitrary weight, can you do the same thing? Yes, I think they would, because they both have this property. They can only compute it once, and once you do, you found it. So I think that actually is true. Yeah.
But yeah, so there's that. And there's also like
Yeah. Okay. Let me draw a quick graph. This is like when you hear about reduction, you're not actually going to do reduction. Basically, what happens is we will give you like some input and say produce some output. Like that's. And we don't necessarily have an algorithm to do this. But what we can do is take your input and convert it into something that looks like something you can. So it's like you're taking your input and changing it, tweaking it a bit, like with a graph, for example. You might have some nodes and edges. You take that input and then run it through some algorithm that you've learned in class. And that's going to produce some output. And then you want to take that output and turn the output back into the original problem. So it's like we give you these, we tell you this is what we give you, this is what we want, and this is what you have to do. This is like what will be expected of you.
So say, if I say this, that reduce to some, I'm kind of confused. I saw in final exam say shortest
Yeah.
and then shortest path circle, and they could say like this reduce to circle.
Yeah.
I mean we have that.
So when you say reduce, so I'm kind of confusing which way do you?
I always get confused on the direction, actually, but basically it is one problem we use to solve another.
Okay.
Because what you're saying is like this problem is.
Oh, yeah.
It's like a very
Is this
similar
problem reduced to this problem, or
but
this
now
problem
you just
reduced
use
I actually always get it wrong, but I think it is actually this problem gets reduced.
So
yeah, so it's good for like
I believe so.
yeah, there's like a
like topological sorting it.
follow that.
You don't have to know.
Oh, because there's like MP.
You don't have to know.
Okay.
Yeah, it's not important. Like what the definition of reduction is. I always forget it, so I'm not going to try it. You don't have to. Yeah, but then you have to do this.
Yeah, I'm just not really sure like what about the LCW.
Sure.
I guess like
It's like, why did we say that it like just converges to like 3/4 or
why did these
was it 3/4?
Yeah, but why did the bees dominate if there's an equal number of basic bees?
They dominate in terms of the outputs. So with the A's, they're getting a lot smaller. So they're going to be a much smaller portion of your compressed output, whereas the B's are actually getting larger. So they expand and they become like they quickly become a significant part of your output. And so they're going to.
But like in the test, I would literally just evaluate the limit.
Like, I understand why they
Yeah.
multiplied by 1/2, but I also don't understand why. I was just like, I get
Yeah,
it,
it doesn't
because it's half of
No, and that's why
yeah,
we
but is
sort of
that like a
hand-wave
rule, like, if we
these little
do the ratio for
till the
half of
equals
So-
that are like it's close to.
So I can also be J technically.
Wait, that doesn't make sense.
By that reason.
Yeah, because it's
Yeah, the ratio, it's like.
Well, it should be the closest.
I
Oh,
see,
wow.
like, I was
Okay, that's
So which
very-
one best?
That's very
Okay.
Which one best represents?
So-
I know it's not clean.
If
It's
we
not perfect.
do this, like
Your answer is going to be like
Like in the
Very
test, I
most
would have
rare.
done that
yes,
and like computed the limit and then see that nothing matches and be pretty worried.
right.
Oh,
Yes,
alright,
so
but we can keep
it doesn't really specify, but keep in mind that generally, I mean, it's very rare
correct.
that this should
Not
happen
even
that you won't get an exact answer. So if you don't get an exact answer, like some of these will be off by one. Like we said, they're 38/48, but they're probably actually like minus one from that.
Mm-hmm.
But so just keep that in mind. But,
have one of
but like it's gonna be whichever.
Okay. Yeah, that's
do you understand the algorithms?
And why, when we do the BFS, do we have to keep track of the distance? Because BFS already does a level order traversal. So like at every single level, you are like you're never gonna have a lesser distance in the nodes that you're checking.
I'm sorry, I
It
love
happens
Starbucks.
because so it didn't show up in this graph.
Okay.
But it actually depends on the order
Yes,
that you
but
use.
like, okay.
Why don't you
But
go
Star- I
study
don't-
What do you mean by the order?
I think.
Because coffee doesn't have the
So yeah, so
ambiance.
I get
I will give that to. I don't drink their
Alright,
coffee.
so yeah.
Their ambiance. I just
Because the solution I
coffee
constructed
is
was
so
exactly the
much
same, but
overcaffeinated.
without checking
It's
distances. Like
coffee
just
powder
literally
is
using
like
BFS,
great.
keeping an array of
Chill,
all the
it's
vertices, and like
it's
saying,
normal.
oh, this one has been checked 3 times. If there's a
Great.
0
Yeah,
in that
you
array,
really fit
I just increase it to 1 and then NQ it to the Q of like the regular BFS.
And the tables are
And if it's 1 or greater, I don't NQ it, I just increase the count. Because if I increase the count, it was already in the
It's the
queue.
only place I could
If
say
you know
Yeah.
what I'm
So if you're
8 hours
if you're
straight.
keeping track of what yeah, if you're using the fact that it's already in the queue and,
Yeah, so
and
for,
updating it like that.
for instance,
Which I guess is what
Yeah,
you're doing
okay.
here.
Probably-
Minus keeping track of the
Yes.
actual distance.
Okay.
Probably,
Um,
actually, Firestone's fine, but the
With
problem with Firestone
BFS
is
that might actually work.
Okay, the reading room in Firestone and the
0,
night
1, 1,
Yeah,
not
because
because those are depressing.
Yeah,
exactly
It's
what
like
we're doing.
you have to get up and
you would
like,
have to
walk
like
at
yeah, you
least
need a way of
5 to 10
visiting a
minutes
node
back.
Oh, yes,
And
that's
that's
true.
a problem.
Yeah,
That's
Yeah,
a real problem.
with a better distance than you've already found.
Which doesn't make
So I
sense
don't think
because
it's-
of the nature of BFS.
because
Like
of the
it's a
nature of
level
BFS.
order traversal.
Yeah. So I think you might actually be right.
Okay.
You might be able to do away with the
So it
distances.
could be,
But distance here, yeah. So it's ignoring weights. Distance is really just
Yeah, I understand.
measuring.
Yeah. Okay.
So yeah, I guess it's
It was just to see if it was actually completely necessary to
Yeah.
keep track of the distance.
no, that's fair. Yeah.
So the
Or
first
2 to
step is counting the frequencies of all like.
So
So how
Yeah,
many
no,
are there
yeah.
total?
Yeah.
the reason
Well-
why we know we can carry this over is because
So
force
what
count
or how
gets,
often
like,
pages are
completed
exact.
before we check
get
in.
I just feel like so
Like-
much of this is arbitrary.
Before we
It
visit
really is,
teams,
like, especially that
we analyze for enough that we know it's
I
not
know,
going to
right?
change anything.
It's like I'm straight up
Because of
gonna
the
lose like
others,
8
and
points
that's
in that problem.
Yes, that is this property.
Yeah.
Yeah, the
Okay.
fact that you DQ a node once.
Okay.
That's why it works if you don't have to read it.
Like whether
Alright.
we can do like 50 iterations.
Yeah, so I guess it's like
Uh,
it's like normally in say Dysis or something, it's like when you visit a
I saw
node,
you
your
doing
distance
that
is
for a
correct.
while.
Here,
I was like,
when you visit a node, like
I
your
still
count
can't
is.
get to
I still don't understand.
I create a Huffman tree.
Yeah.
And that's
Thank you.
basically
Cool. Yeah.
so I
Hi Ross.
Yeah.
Could you explain why you multiply by 1/2? Because I mean,
So,
we like
for
understand why you
instance, what would
have
be
to,
this
but
policy?
also I don't understand why you
One
multiply.
and one. So I put D and
Like,
S
it's-
together.
So
these two
it's because
combined
of
have frequency
the
of
fact
two.
that that
So
sequence of B's
those
only
new
represents half
nodes,
your
which
Uh-huh.
ones do
total
I want?
sequence. So
You
given
keep the
any
1 and the
string
2,
of length n,
Mhm.
only half of those
And
characters are going to get
take
increased by
A,
that much.
and then 2. Okay, that's
Oh,
great.
so if you
So take
you
A,
multiply by the proportion.
and
So if you calculate the
together this
ratio
has
for
a
like a
frequency
proportion of the
4.
string,
Right.
So
you have to
now
like
what do I-
multiply.
You should multiply by
the
that
rate-
proportion.
Okay.
Yes.
That's, okay.
Right,
That's
exactly.
That's
So
right.
not
let's see.
intuitive to me, I guess.
No,
And
it's,
then I
it's totally
grab
fair.
numbers.
I mean, it's a little bit hand wavy
Yeah.
because we're sort of ignoring the A's
So
entirely,
now,
but really you
what
could
I
compute it with the
do
A's and
is
you
Yeah.
get something
get my
slightly
actual
better.
encoding.
Uh huh.
I
But we
say,
kind of hand wave over that.
Okay.
I'm
Alright.
gonna put these in boxes.
Wait, about that, so like,
Um,
for like all the B's
if I go
you
left,
see, right, so they're n
I
over 2
encode
of them, so
0.
you would say
If I
like
go right, I
um,
encode
12
Left
Left
So-
is always 0 or
left is always 0. So in this
Times
case,
n
I
over
would
2
label
over
all of my links
8
in my
times
tree as
n
zeros
over
and
2,
ones.
right, so doesn't it cancel?
You only
So
multiply it by
I
a
start
half
the
once.
I try to
But
go
I'm
to
saying, like,
leave
if I want to
whatever
encode like n
zeros
over
and
2
ones
B's,
that I
right,
come
each
across,
of
that's
them
my encoding for
is
the letter.
12,
So
and the
for the
original
word
was
or
8.
the
Yeah, yeah.
just the letter.
So
Yeah, so each of them is going to be 12 over
For
8.
instance,
Oh, so then you go
Yeah.
to AC.
And this is a ratio
X
looking at your
and
entire
see how many
sequence.
zeros and ones
So
there
in
are.
your
Maybe
entire
there.
sequence,
yeah, you take that
only
exact
half of
bit
your
string.
sequence
So for instance,
will get
what would
this ratio.
A-
Like
it
this
would
only
be
applies to half of your
1,
sequence.
0.
Perfect.
That's why you multiply
And what
that.
about B?
B
so
is
is
0,
this kind of
1,
like
C
doing
is 0,
the
0, D is 1, 1,
expected
0,
value
X
where
is
like
1,
this is the weight and this is the weight and then like
Okay.
this
Easy.
proportion is like half and half.
And then
As
what
in,
was
like-
the last one?
Kind of, it's more like you're taking a limit.
So
Like you're looking at what happens as n
LCW,
gets really large,
the idea is I
and
would
you have the
dynamically
part for the
add
A's and the part for the B's, and as n gets larger and larger, it's going to get closer to
Dynamically add to it. Okay.
12 eighths, or
So
times
the
a half.
idea for encoding
Like the
is,
full thing, if you account for half
so I have
are A's and
my,
half are B's,
original
and you do the whole equation, so
256
each part is getting
characters with their respective encodings
multiplied by a
whatever. Oftentimes you'll see like it starts off with B, because B is like the
Do you have any other
end of
questions?
line or something.
Oh, let me stop this stream.
I guess
So
the